probably the main reason why zirconium alloys are used extensively throughout nuclear reactors is that they are very neutron transparent. And then this over here at high niobium content is really interesting. This is what we call a miscibility gap. So if you're, say you have a 60% niobium alloy, if you cool down into this region, you'll get a beta and beta microstructure. If you apply a strain to this microstructure in the direction indicated by these arrows, you can squish the atoms around in a very rigid motion like this until you have a 60-degree angle. And now, if you look at this deformed BCC crystal, this is an HCP crystal structure. Because there's this really precise orientation relationship, you can actually see with your eyes, we call them prior beta grains, they have all of these different orientations sometimes have a similar reflectivity.
Hi, Joe. Hi, Niels.
Hey. Hello, Peter.
Welcome to the podcast, Everyday Metallurgy. Today, we are digging into a world that most people do not even know exists, because we're going inside one of those machines that you rarely get access to look into. We're going to talk about materials that are used in nuclear plants, zirconium alloys. And we will dig not only into the machine, but into the material and go into the microstructure to learn more about how they are shaped and how they behave. I have invited Niels. Niels is a friend of the house. He has been on a few episodes before talking about microstructures, and Niels will assist me because I'm a no-brainer in this field. So he might ask the right questions to you, Joe. But Joe, could you present yourself and tell a little about your background?
Yeah, so my name is Joe Wendorf. I'm a zirconium metallurgist at ATI. We are a specialty alloy supplier, so we make all kinds of different alloys for niche applications. Everything from rocket engines to nuclear reactors to jet engines, all those kinds of advanced things. If it's difficult to melt and difficult to process, and it's a metal, we probably make it.
Yeah.
So yeah, I was going to talk today about some zirconium alloys that we make that go into nuclear reactors. My background is I got my PhD at UC Santa Barbara, where I studied fatigue and titanium. And then I've been working at ATI for a little over 2 years now, where I've transitioned into zirconium. Maybe this should have been obvious in hindsight, but I definitely didn't know at the time that kind of the fundamental concepts, metallurgical theory behind zirconium alloys and titanium alloys is very similar. They have very similar phase diagrams, similar microstructures that can be achieved. So it's been really nice to be able to come up to speed quickly over the past 2 years on these zirconium alloys, and I'd like to share some of what I learned with you.
That would be fantastic.
Thanks very much.
Yeah. Should we dig a little deeper into the background of it?
Sure.
What are they used for? Where are the applications found?
Yeah, let me share some slides I've prepared here. All right, so the alloy I've chosen to talk to you about today is zirconium niobium alloy. I chose this because it's a simple binary alloy that keeps the phase diagrams a little bit easier to understand. But we make many different types of zirconium alloys for different applications, some of them nuclear and some other applications. So the particular application that I want to share for these zirconium niobium alloys is a type of nuclear reactor called a Canadian deuterium uranium reactor, or it's abbreviated CANDU, C-A-N-D-U. So probably the main reason why zirconium alloys are used extensively throughout nuclear reactors is that they are very neutron transparent. So when you have a fission reactor going on in a nuclear fission reaction going on, you have a neutron that hits an isotope called uranium-235 that splits and 3 more neutrons are generated. And running a nuclear reactor is all about making sure that one of those 3 new neutrons triggers another reaction.
Yeah.
So the more neutrons are absorbed in the walls of your reactor and other structural components, the more you need to enrich your uranium fuel in order to maintain that fission reaction in a consistent manner.
Yeah.
So essentially, the more zirconium you use and the thinner you can keep the components, the less expensive your fuel is and the cheaper it is to produce power. So that's the main reason why these alloys are used. And any alloy that has a lot of zirconium will accomplish that, although there are some impurities that you really need to keep low. In particular, hafnium is a impurity element that is in zirconium ore that is very strongly neutron absorbing, and so we go through a lot of effort to take all the hafnium out that we can.
Yeah, is it like lead? That's also an absorber, isn't it?
Yes, I'm not sure. I think it's stronger in terms of, so we have a parameter called the neutron cross section, which says how likely a particular atom is to absorb a neutron or not. I'm not sure if hafnium is more absorbing than lead, but one of the really bad things about hafnium is that it can absorb 5 or 6 neutrons before it becomes radioactive and turns into some other element. So that's a really important impurity that we need to remove.
Yeah. And the hafnium is named after the capital of Copenhagen, or the capital of Denmark, Copenhagen. So, and that's where Niels is today.
Yeah, close to at least.
Okay.
So it's a little appropriate.
Great. So yeah, that's why zirconium is used. But then a particular component in these CANDU reactors is called the pressure tubes, which these tubes are used to hold the coolant under high pressure so that it's a heavy water coolant, deuterium oxide. So chemically, it's very similar to water, but it has different neutron absorbing and moderating properties than water because it uses deuterium instead of hydrogen. But just like water, it boils at 100 C. And so these pressure tubes allow them to pressurize the water that can then allow the reactor to run at 300 Celsius, which helps with the efficiency of the reactor.
Yeah.
So these tubes hold this water under very high pressure. It's about 100 atmospheres of pressure in order to raise that boiling point, right? Just like if you go up on Mount Everest, the boiling point of water goes down. Well, if you go to really high pressure, the boiling point goes up. And so the water is a liquid at these operating temperatures, and it can pull a lot more heat out of the fission reaction than a lower temperature coolant loop.
Yeah. A question, you said it was transparent. Does it mean that it goes through or it just pings off?
Yeah, so in the case of zirconium, it's very transparent to neutrons, and they can penetrate, most of the neutrons can penetrate straight through these zirconium pressure tubes and other zirconium components.
Yeah.
Think of it like light going through a pane of glass.
Yeah.
But then the heavy water, it's a little bit more complicated. The heavy water is used instead of normal water because when the neutrons go through it, they slow down without being absorbed. It's called moderation.
Yeah.
So you have moderation of the very fast neutrons that are generated by the fission reaction into slow neutrons. They're called thermal neutrons, which are then much more likely to interact with other parts of the uranium fuel. So the water helps slow the neutrons down without absorbing them, and then the zirconium is just very transparent, so that the neutrons can pass straight through.
Yeah.
So, but you say the neutrons pass straight through the zirconium, but you still have a likelihood of some radiation damage to the zirconium.
Yes.
Is that right?
That's correct. So nothing is 100% neutron transparent. There are still some neutrons that are absorbed. It's a matter of how many are absorbed. And then when a neutron is absorbed, you're exactly right. It can cause dislocations and vacancies to be injected into the material. It can also do some really crazy things called transmutation, where a neutron hits a zirconium atom and then it transmutes into another element, usually niobium. So there's a lot of unique metallurgical considerations that, usually when a metallurgist makes an alloy, they're not thinking about the elements they put into the alloy changing into other elements, but that's something we have to think about in this application.
That's called alchemy.
Yeah.
But yeah, in all cases, the lower your neutron cross section, the more neutron transparent it is, the better off you are because there are fewer of those irradiation damage events occurring.
But you do rely on some impurity atoms for strength so that you can harden the material, right?
Yeah, and we'll get into that.
Yeah.
So yeah, we have these requirements of a low neutron cross section. Because of the high pressure and high temperature, these need to be very creep resistant. And then another important requirement of these alloys for the pressure tube material is that they have to be corrosion resistant. In particular, hydrogen in the form of deuterium from the heavy water coolant can ingress into these materials and cause zirconium hydrides to form. And so we also need to process this alloy in a way that resists that hydrogen ingress. And when hydrides do form, we want them to form in a certain direction that maintains their fracture toughness. Yeah. So here's a picture here of the kind of the ends of all the pressure tubes in a CANDU reactor. And then the fuel is packed in these little cladding tubes that is put in the ends of these pressure tubes. And the cool thing about CANDU reactors is that they can take a new fuel bundle and put it into the end of the pressure tube, and the old fuel bundle will pop out the other end, kind of as I'm showing this diagram here. Yep.
Yeah.
So you don't have to fully shut down the whole reactor to refuel. You can kind of refuel iteratively, and then when you put a new fuel bundle in, it'll push all these little orange fuel bundles down the line, and then they'll come out. And that's what these kind of arms here are indicating, how they pull the fuel bundles in and out. And then the cooling water flows through these pressure tubes and goes to a heat exchanger where, it heats just some normal water, non-heavy water, and turns into steam and runs a steam turbine. So that's just like any other power plant, coal power plant, oil power plant. You generate steam with the heat and turn a turbine. So that part's very typical.
And the black lines you have named number 3, is that the moderators?
Yes. So that's I'm not a nuclear engineer, so I only have a very basic understanding of this. But basically, you need to stay right on the threshold where for every fission reaction, one of the 3 neutrons causes another fission reaction. And so if your fuel is very slightly too rich, you'll get a runaway reaction where maybe 1.1 fission events are generated for every fission event. And so that'll just exponentially grow. So that's what these control rods here, which often are made of the hafnium that's pulled out of the alloy. I mentioned earlier, hafnium is really neutron absorbing. So there's many materials they use. There's many materials. Sometimes they're graphite, sometimes they're hafnium, sometimes they're other materials. But some neutron absorbing material. They also can inject boron ions into the cooling water, which is a very neutron absorbing ion. And so, so the hafnium or other neutron absorbers are in these control rods, and by inserting these control rods more or less, they can fine tune the rate of fission to get that exactly at criticality, exactly 1 fission chain reaction per reaction. So that's what those are for. But you want the rest of the reactor that's not the control rods to be as neutron transparent as possible, so that it's as easy as possible to get to that critical state.
You both have a speeder and a brake in this machine.
Yep, and that way you're able to control it and maintain a precise level of heat output. All right. So we can get into the metallurgy now if you're ready.
Yes, we are so ready.
All right, so let's start with the zirconium niobium phase diagram. So right here I've got pure zirconium on the left and pure niobium on the right. Up at high temperature, we have the liquid phase, and as you cool down, it solidifies into a body-centered cubic crystal structure, which I'm showing here. And this is a disordered structure where you just have a random chance of zirconium or niobium at each lattice site. And then one of the really cool things about zirconium is that it undergoes a solid-solid phase transformation as you cool down. So as you go colder, below depending on how much niobium content, 866C down to 600C, you'll start forming a hexagonal alpha phase. And so it's kind of similar to steel, where steel solidifies in one phase, but then as you cool down, it goes to another phase. Same thing's going on here. We've got a cubic to hexagonal transformation. And you can see that the alpha phase is this tiny little region over here. It can't dissolve a lot of niobium. So at equilibrium, if you have more than 0.7% niobium, you'll have a mixture of alpha and beta at room temperature, where the alpha is very zirconium rich and the beta phase is very niobium rich. So that's this region down here, where you'll have a two-phase alpha plus beta mixture. This little triangle up here is also a two-phase alpha plus beta region. And then this over here at high niobium content is really interesting. This is what we call a miscibility gap. So if you're, say you have a 60% niobium alloy, if you cool down into this region, you'll get a beta and beta microstructure, where you have two different beta phases. So they're both BCC, but one, follow your tile line over here, will be very zirconium rich, and one will be niobium rich. So that's called a miscibility gap. And there's a lot of, even though the alloy I'm going to talk about has 2.5% niobium. So even though we're over here in the diagram, there are portions of the microstructure where it's enriched in niobium to these levels, and we have to understand these miscibility kinetics, where you basically get just two different beta phases, where the only difference is how much niobium is in the beta phase. So that there's not a lot of alloys that have miscibility gaps like that. That's kind of a unique thing about the zirconium niobium phase diagram.
And what does it do? Does it create a lot of micro what is that called, particles? Is it segregating out to make it very fine in the structure?
So in the case of zirconium with 2.5% niobium, the interesting thing that this miscibility gap causes is that if you equilibrate in this, let me make sure my pointer is showing. Laser pointer. If you equilibrate in this triangle here, your beta phase it's enriched in niobium, but it's enriched to 10%, or if you cool down, it goes up to 19%. But then once you drop below 620 Celsius, the equilibrium concentration of the beta phase suddenly shifts from 19 to 92% niobium. So there's some really interesting transformation kinetics where if you age this alloy below 620C, how the beta phase responds to that, and how does the niobium content jump up to the new equilibrium. It's not a slow, steady process. It's a sudden jump. And you can kind of think of it like three separate phases, where you have the alpha, you have the zirconium, the 20% zirconium beta, and the 90+%. The 20% niobium beta phase and the 90% plus niobium beta phase, where there's this complicated pathway to get from the zirconium rich beta to the niobium rich beta. And so in the case of CANDU reactors, where we have a 2.5% niobium in this alloy, and we control the processing to get a certain distribution of alpha and beta phases to maximize the creep resistance. So that's the main advantage of zirconium niobium alloys over a lot of other zirconium alloys, is most zirconium alloys are single phase. They're all the alpha hexagonal phase. But with the addition of this niobium, which stabilizes the beta phase, we can maintain a little bit of beta at room temperature, or 300C, where the reactor is running. And that provides a lot of creep resistance. So the material swells more slowly. Those pressure tubes swell more slowly, and they have a longer life. So that's a basic overview of the phase diagram. Were there any questions about that?
When you say swell, is that that you have grain growth?
So the problem is when you have your fuel bundle inside this pressure tube, you need the water to flow very close to the fuel in order to extract the most heat. If your pressure tube creeps and swells, then the water will take the path of least resistance. It'll flow around the fuel and it won't actually cool it down. So that's one of the main mechanisms that causes a reactor to be shut down for maintenance or eventually just completely retired, is these pressure tubes swell too much due to creep, and the water doesn't cool the fuel down anymore adequately. And so that's why so much work has been put in to slow down the creep rate, is to keep the water cooling down the fuel.
What is the designed lifetime of such a machine?
So there's a new generation of CANDU design where they're trying to increase this, but currently these reactors are designed for the pressure tubes to last about 15 to 20 years, and then they'll do a really long maintenance period where they replace all the pressure tubes. It's called a retube, and then it'll run for another 15 to 20 years. And then at that point, you start having other maintenance issues in the reactor, and so you get usually one retube, and that kind of sets the lifespan of the reactor. So you have these really high upfront costs, you have a high cost to retube, and then you have the fueling costs, and that's kind of your lifetime cost to run the reactor. So if you can improve the creep rate,
what happens to the alloys when you replace them? Can they be recycled, or what do you do with them?
What happens to the irradiated pressure tubes?
Yeah.
That is a good question. I know a lot of them are studied in great detail at Canadian nuclear laboratories, where they examine these irradiated tubes. They have special labs where they can characterize after running for 20 years in a nuclear reactor, these tubes themselves become radioactive. And so you need special handling to be able to study them. Like they have microscopes where the microscope only handles radioactive material.
Wow.
So I know a lot of them are diced up, and they do sampling to make sure that the material is still safe to use in the reactor. But as far as the ones that aren't used for research, I actually don't know what is done with them. We certainly don't recycle them into new pressure tubes because they are radioactive at that point.
Yeah,
that's a good question. I don't know the answer to that.
So you have to dispose of them in one way or the other. Interesting.
Yeah. I would guess that they are just stored on site for a period of time until they have a safe level of radiation, but I'm not sure on that. Because the danger of the irradiated tubes has a half-life like any other radioactive material, and so if you wait long enough, it decays to a safe level. But I don't know the details of how they handle that.
Joe, could we look into the microstructure of of the material? I would love to see that beta.
Yeah. So because this alloy only has 2.5% niobium, I don't have a beta plus beta microstructure to show you. You'd need at least more than 20% niobium to see that.
Yeah.
But I do have an example. So this is an as forged microstructure. So we melt this alloy into an ingot, and then we do some processing. And then if you do forging in this kind of triangle of the phase diagram, and then air cool, you get this microstructure. So this really shows the alpha and then the 20% niobium beta phase. So here we see alpha grains in the microstructure with these beta, much finer beta grains in between. And so you can see how the forging has caused, basically what happens here is when you're forging, you get a dynamic recrystallization. And so you get a very fine microstructure of alpha grains with these beta grains in between.
Yeah. So this is from drawn tubes, is it? This
is part of a forging. So this is the, how do I put this? So this is not a tube yet. This is like a forged log, we call it. So this is a large log of zirconium
and
that requires additional processing to become a pressure tube.
And you are forging it at that low temperature?
We have a couple different forging steps, and one of them, yes, is forging here. The reason we forge it at this temperature is to form this fine
this recrystallization, in situ recrystallization, you could call it.
Yeah. So when the ingot is melted, which we have to melt under vacuum because zirconium is a very reactive element. So we do a vacuum, it's called vacuum arc remelting, VAR. And at the end of that process, you have very long columnar grain structure that has a lot of variation and isn't consistent in its properties just because of the very large grain size. And so by forging at this temperature, we're able to refine the microstructure to a more homogeneous state with these very fine alpha grains.
Yeah. So I'm guessing when I look at the phase diagram, there's not a lot of segregation during solidification, but of course you will have these large columnar crystals.
Yep.
So homogenization should be not so complicated.
Yes, homogenization is usually less of a concern than getting a consistent grain size and morphology.
Yeah.
Exactly.
So how does it deformation harden? Sorry, it's not just deformation hardening of these materials compared to steels, for instance. Is that similar?
So this particular alloy is fairly ductile and has a lot of strain hardening.
Okay.
So I would say it's much softer than your typical medium carbon steel, and has a significant degree of strain hardening as you go through all of that plastic strain up to your ductile limit. And that's part of why we forge it in this way, is that when you have really large and coarse microstructure, certain grains will deform differently than others. I mean, that's true when it's a fine microstructure as well, but when you have a very coarse microstructure, that deformation is less homogeneous. Certain grains will deform more than others, and you'll see wrinkles and shear bands in your alloy that kind of limit how much ductility the overall alloy has, because your ductility is concentrated into individual grains, whereas here we can distribute that deformation more evenly throughout the microstructure.
Typically when you see forging, you can see the forging direction, but here it looks I cannot see how it's forged.
So here, if you imagine that the forging looks like so it's a radial forging technique that gives you a round log, and we've kind of cut a circular cross section through that log. So we're kind of looking end on at the microstructure. If you were to cut a cross section down the length, you can see a little bit of that grain flow. But the grains are so these grains are elongated, kind of out of the screen here.
Yeah.
But they're fairly they're not as elongated as I don't know how to put this. They are elongated, but their aspect ratio is maybe 5 to 10 as opposed to like really long elongated microstructure.
Yeah, I'm familiar with tool steel, where you can often see something 100 microns long and 5 microns thick.
Yeah. But I'm guessing that when you have made the tube, there's much more deformation in the material, and then you'll probably have more elongated grains.
Yes.
Would that be right?
So there's forging, and then there's heat treatment, and then there's extrusion of the tube. And so after this, there's a lot more deformation that goes into the microstructure. And then what I think is really fascinating about this alloy is we do something called a beta quench. So that's on my next slide here. So now we take this forged piece, we heat it up into the beta phase, and then we cool rapidly. And what we see are these very fine lath-shaped grains, and there is no It's a single phase. But what's fascinating is that this isn't the beta phase that has been frozen in. These are alpha grains where there is no beta phase in between them. And so the explanation for how that happens is actually really fascinating. There's a Martensitic transformation that I've made a little animation to explain. Yeah, so here if we zoom out, this is just this is an electron microscope micrograph where we see these really fine laths that are, a few microns thick.
Yeah.
But if we zoom way out, where this is now 1 millimeter, these alpha laths have arranged themselves into these larger structures that looks just like an equiaxed grain structure, right? So the explanation for this is these are something that's called a prior beta grain. And so I'll try to explain that to you now with this animation. So when we're at high temperature and the material is in this BCC beta phase, there's a Martensitic transformation that it goes through where there's a relationship between the beta phase and how it transforms into the alpha phase. So I'll explain that here. Here is the 110 plane of the BCC crystal structure. So here, this diagonal here. So we got an atom on each corner and an atom in the center that I've shown right here. And if you measure the dimensions of this, you have your lattice parameter and then square root of 2 times that, just because you've got a 45, 45, 90 triangle here.
Yeah.
And the angle, the bond angle between nearest neighbors is 70.5 degrees. But the amazing thing about this is that if you apply a strain to this microstructure in the direction indicated by these arrows, you can squish the atoms around in a very rigid motion like this until you have a 60-degree angle. And now, if you look at this deformed BCC crystal, this is an HCP crystal structure.
Cool.
Yeah, so there are some more details that I'm glossing over here about how this second plane of atoms deforms. But basically, if you apply a strain to the BCC crystal structure, you can deform it into an HCP crystal, which is the alpha phase. And this is actually a very general trend across a lot of different alloys. Like, for example, in steel, there's a way that you can strain austenite to become ferrite. And that's how martensite is formed. And then there's also one for FCC to HCP. So there's these strain pathways that connect the different crystal structures together. That is really fascinating. And so if you show both of these crystal structures on top of each other, here I've got the BCC in gray and the HCP in blue, you can see where the atoms start and where they move. And there's no dislocations needed to accommodate this. There's no nucleation and growth mechanism. You can just deform one crystal structure into the other. And there's something called an orientation relationship where basically if you rotate the BCC slightly, you'll see that some of the directions in the BCC structure align with the HCP structure. You can also rotate it this way, you get a different alignment. And so there's basically different strain pathways you can take to transform BCC into HCP. And so to summarize that up, there are 6 different 110 planes in the BCC crystal structure that become the basal plane in HCP. And then there's those 2 111 directions in each of those planes that can become the A direction in HCP. And so when you multiply those together, there's 12 different variants. So here this diagram is showing a BCC unit cell, and then in blue are the 12 possible alpha variants. These are called the Berger's orientation relationship. And so that's what's going on in this microstructure, is these are the high temperature beta grains. And then when we cool very quickly, we don't allow the alpha and beta phase to equilibrate like we did during the forging. The beta just turns directly to alpha. The niobium is trapped in a supersaturated solution.
Yeah.
So you have alpha phase with more than 0.7% niobium contained within it. And each of these little laths is a region of the prior beta grain that is transformed by one of those 12 variants into a tiny little alpha lath. And so this gets us, what it does is it helps randomize the crystallographic texture that is produced during forging. So we get grains of all different orientations. And they're these really fine little laths that, when they're extruded into a pressure tube, help get to an optimal microstructure, which is a little bit more complicated. So I'm trying to keep it simple here. But I just wanted to share that BCC HCP Burgers pathway with you to explain how we get this really fine lath-like microstructure.
Yeah, and this is supersaturated niobium.
Yes.
Does that precipitate during heating up, or is it not?
So what happens during when this microstructure is then extruded into a pressure tube, the niobium comes out of supersaturation into beta precipitates.
Small nanoparticles.
And there's a lot of detail that I'm still trying to understand about how the niobium comes out, and does it form this kind of 19% niobium beta phase, or does it go all the way to the 90%? It depends on how you age it after extrusion, how much deformation you have during extrusion. It gets very complicated after this step. Yeah, it's just it helps us to, it's helpful in the extrusion process to have the niobium supersaturated in the alpha phase, because then we can control the extrusion process to pull that niobium out in a controlled way, as opposed to having those really large clumps of the beta phase in the as forged structure.
Okay. Yeah. So you are, is it cold extrusion, or is it, do you extrude at 400 or 500 degrees or something like that?
I can't share the exact temperature, but it's in this triangle here.
All right.
Yep. Also, ATI doesn't do the actual extrusion. We have a customer who does the extrusion. There's a complicated supply chain here, but this is the structure of the material when it leaves ATI. Yeah. So, and it's really amazing that you can actually see these, because there's this really precise orientation relationship. You can actually see with your eyes, we call them prior beta grains. They have all of these different orientations sometimes have a similar reflectivity due to the optical anisotropy of the HCP phase. And so you can see with your eyes these large prior beta grains, which is pretty fascinating. So it's on one hand you can see the microstructure with your eyes, but on the other hand there's these ultra fine, submicron grains, which is pretty interesting. Also, you may notice at the prior beta grain boundaries, we have a very aligned structure of these alpha laths. So I said earlier that no nucleation mechanism is necessary to do this transformation, but there is still a little bit of a nucleation effect on the grain boundaries, where it happens first at the grain boundaries, where usually there's one, when you look at your two beta grains across the grain boundary at high temperature, usually there's at least one alpha variant, right? So you have two different cubes here, but there's usually at least one variant that is common between them, or with a low misorientation. And so that variant will form at these grain boundaries and form a grain boundary colony of alpha laths.
The precipitates, are they so small that you cannot see them?
It depends on the processing. If you were to just age this microstructure, so just take the beta quenched material and do an aging process, you would form very fine precipitates that you would probably need a transmission electron microscope to see. We wouldn't be able to see them in our SEM here. But in the extrusion process, when there is all that deformation going on, we do often see some larger beta, like what I would call a beta grain instead of a beta precipitate, forming between the alpha grains.
And if we look into the product itself, what are the properties of it? This is done to secure that it's creep resistant.
Yes.
But what is the what are the general mechanical properties of the alloy after this process?
We have there's a thing on atimaterials.com where we have all the properties. I don't off the top of my head, because it depends on processing, right? So I don't off the top of my head know all the properties, but it's generally if you're comparing to steel, this material is not as strong as steel. We've got again, it depends on processing, but maybe around a 300 MPa room temperature strength. But it's very ductile, and it maintains that strength up to 300 C, which a lot of zirconium alloys cannot maintain that high of a strength up to 300 C.
Yeah. Okay.
And then I think I had one more slide here. Yeah, I just wanted to give. So this is a different alloy, but it's a really beautiful heat tinting technique that our metallographer Brad Webb does, just to kind of illustrate the different orientations that are going on here. So you can see this is a prior beta grain, and then all of the alpha laths in this grain. There's only a couple different orientations that are present. You don't have a whole distribution of orientations. There's very specific orientations, and then you can see when you go to this prior beta grain, it's a different subset of orientations that are present. And you can see a colony here on the prior beta grain boundary as well. And yeah, so the color here is basically related to the oxide film thickness. It's like a thin film interference effect. And so different orientations will oxidize at different rates. And so this this shows you those different alpha orientations. You don't see every color.
I thought it was EBSD.
No. This is optical.
Yeah. Wow.
It's super nice. It's like a piece of modern art.
Yeah, absolutely.
One of the expensive ones.
Yeah. Our metallographer here is incredible, and both a scientist and an artist for sure. If you guys are interested in learning more about this material, a lot of Brad's micrographs are in this textbook, The Metallurgy of Zirconium by Kit Coleman. And there's a free PDF that you can get on the iaea.org.
I actually downloaded it, and I had a look at it. It's a super nice book. There's a lot of work in that, a lot of knowledge in that book.
Yeah. So volume 1 goes into a lot more detail of how pressure tube manufacturing is done, if anyone wants to learn more. This is the original paper by William Burgers, where the Burgers orientation relationship was first discovered back in 1934. And then this paper by Lugering it's about titanium, but like I said at the beginning of the talk, titanium and zirconium are very similar in terms of the fundamental theory, and it goes through a lot of detail about how we can control the microstructure through processing. So for example, you can see that the laths here are a lot coarser than the laths we see in niobium. That's because the cooling rate is different. The slower you cool, the larger these laths will be. And that has implications on the strength, ductility, fatigue behavior. And this paper here goes into all of those details in a nice summarized form. And then here's my email address if anyone has any questions.
Great. Joe, I have a final question before we end today. The podcast is called Everyday Metallurgy. So are there any places in our everyday where we will meet some of these alloys?
Well, every time especially if you live in Canada, although there are CANDU reactors all over the world, anytime you turn your lights on or use power, some of that power may have been generated by a nuclear reaction inside one of these pressure tubes. So I think that's an important application. Because of the corrosion resistance of these zirconium alloys, a lot of them are used for medical applications. So there are different types of zirconium, like hip implants and devices like that.
Yeah.
And then this concept of the Berger's orientation relationship and Martensitic transformations, those are used in a whole different range of alloys. For example, shape memory alloys are a good example where they use these precise orientations to be able to remember the shape that an alloy was in before it was deformed. When you go back to the beta phase, you'll recover that shape. And so that mechanism is used for stents for
the nitinol
heart surgery.
alloy.
Yeah. So these are used. This is a concept that applies to all kinds of different alloys that are used all throughout our everyday life.
Fantastic. Thank you very much.
Thank you.
Yeah.
Niels, thank you very much. It was super interesting.
Yeah, my pleasure. I really like sharing these concepts. I really think they're interesting from a theoretical perspective, and it's really interesting how we can apply these Martensitic transformations to target certain properties of the alloy.
Yeah, and for me, it's an entirely new world. In Denmark, we don't have nuclear plants, so we never learned anything about these materials and why they should. So my questions were not because I was polite. It was because I really didn't know.
Okay.
Yeah, it's as true as Peter says. These are materials we never see in our daily life, and also it's a. I mean, from a more fundamental point of view, the phase diagram is different. There are things going on in that phase diagram that you don't normally see in materials either. I find that super interesting.
Yeah, I really am interested in titanium and zirconium because of that complicated phase diagram. I think the solid transformations they give you so much more flexibility. Because of how you can control the microstructure through that transformation, that's what makes these alloys so flexible through processing to target different properties. That's part of why steel is so ubiquitous, because it has a similar right? And then
I was looking at
you can get.
Yeah, I was looking at the book on zirconium alloys, and there's some TTT diagrams. And from a simple phase diagram as what we're looking at, is quite amazing what you can do with TTT diagrams for different phases. And it's very versatile in that way.
Exactly.